We know we need to reduce energy and communications inside large machines. The power dissipation of those machines is a major limitation, and arguably most of the energy is dissipated in the communications. This is true from the level of connections on the chip between gates and for all longer distances. Now, optics has the potential to solve this problem and to give us the necessary bandwidth densities, and we have a very large amount of headroom in optics to increase bandwidth densities. Indeed, optics has the potential to reduce communication energies by many orders of magnitude, and this is particularly true for all interconnects from the edge of the chip and all longer distances. Of course, we already know and exploit optics for kilometre and longer distances, but once we approach the chip, the targets, especially for energy, become tougher for optical connections, at least as we currently try to engineer them. Current communication energies off the chip are in the range of a few picojoules per bit, both for optical and electronic connections. We are, of course, considering how we can push this down more towards a few femtojoules per bit, which would transform power dissipation in large systems. If we stand back from the details, what is it in the physics and the technology that prevents us from getting to a few femtojoules per bit? As is often paradoxically the case in making major advances in applications, it turns out that there is indeed something we have to stop doing. We need to understand what actually is the source of most energy dissipation once we start looking at shorter distance connections. Essentially, in electrical and optical systems, we need to figure out what precisely is it that we're doing that dissipates all this energy, and we have to stop doing it. For this talk, there are a couple of useful major references. First of all, this paper goes into a lot of detail on energy, systems, and device physics. And this paper here gives some additional detail on waves and channels for optical communications. Incidentally, I'm always very happy to send people copies of these slides, and if you would like them, please email to this address. So, what is it we have to stop doing? And why does that help? And of course, what is it that we have to start doing instead? Well, it's common for device physicists and engineers like myself to presume that the answer is that we need new physics for lower energy devices. So then, do we need some new physics here? Well, unfortunately for my job security, the answer to that question is no. We don't need some magical new effect or some new phenomenon to be discovered or some magic material to be created. We have the physics we need in order to move ahead. And in fact, this physics is good enough to move ahead for some time. We already have good enough devices, though we do need to develop the technology to exploit them. And in my opinion, we need to go beyond the devices and technology we're currently using in our commercial processes. For example, germanium quantum well modulators on silicon. There are research demonstrations of good technology in multiple labs, including at least one foundry operator. And this approach needs no resonators or tuning power, so it's very attractive from a systems point of view. And it's already capable of low energy and high speed operation. And I think there are other examples of viable devices. We have these devices. So here is one example of this kind of device. It's a germanium quantum well modulator grown inside a silicon waveguide. It's only about 10 microns long. As I said, it's on silicon. It doesn't need any resonator to work because the effect behind it, the quantum confined Stark effect, is extremely strong. It only requires about 3 femtofarads of capacitance, and we'll see later why that's an important number. And it only requires a dynamic energy of about 3/4 of a femtojoule to run. So, even being more realistic on total energies, this is a femtojoule grade device. Here's the reference to this work and the energy calculations, and there's been recent progress towards foundry fabrication and other recent demonstrations of this technology. So this is an example of a technology that's sort of ready to go and would give us the next level of performance. A second key point is that optics offers massive numbers of channels. Now, this is not something that we've been using so much already in, say, fiber optic systems. We have large numbers of fibers, but not the kind of massive numbers that we could do with channels in optics. For example, going to multi-spatial mode communications in fibers can get us a factor of 10 or so, possibly more. Going to wavelength division multiplexing can get us a factor of tens or hundreds or possibly more in terms of the available number of channels. And going to free space array connection can get us factors of thousands up to even millions of channels. We can make a very large number of channels in optics. Now, why is it that we're talking about this headroom in the number of channels? It's because we're going to need to use them to reduce energy. Now, that may seem a strange thing. Why is that? To see this, we need to understand what actually is a source of most energy dissipation once we start looking at shorter distance connections. And as I said, once we find that, we have to stop doing it. Why is it that we end up with picojoules per bit in energies for off-chip interconnects? Well, in electrical systems, the answer is really quite simple. It's because we have to charge centimetre lengths of wires, and that takes picojoules because those wires have picofarads of capacitance. Optics fundamentally avoids this. We just have to charge the photodetector to the desired signal voltage. And that's a process sometimes called quantum impedance conversion. Quantum impedance conversion is a very straightforward idea for people who are used to optics. Basically, the photoelectric effect means that we can generate a large voltage in a detector, for example, a fraction of a volt, with very little signal power or energy, and very little classical voltage in the light beam. For example, a 1 nanowatt light beam has less than 1 millivolt in it. But if we shone that onto a photodetector with a large load resistor, we could generate some fraction of a volt. And that's called quantum impedance conversion. Optics only has to charge the photodetector and the transistor to the logic voltage, not the interconnect line. It's useful now then to look at just what are the capacitances inside the system, because these are going to set the amount of energy we need to use, the number of electrons we need to create to charge or discharge these capacitances. So a conventional photodetector is something that may have of the order of a picofarad of capacitance. That corresponds to something of the scale of 100 by 100 microns. Some small photodetector, maybe 5 by 5 microns, might only have 4 femtofarads or so. A wire has a capacitance of about 2 picofarads per centimetre or 200 attofarads per micron. The input capacitance of some small field effect transistor, however, is only of the order of 20 to 200 attofarads or something like that. A 1 micron cube of semiconductor, such as we might have in a small photodetector, itself only has of the order of 100 attofarads of capacitance, so it's comparable to the capacitance of a wire that's maybe a few microns long. Hypothetically, if we could go down to a 100 nanometer cube of semiconductor, we would get, say, a 10 attofarad capacitance, and a 10 nanometer cube would have only 1 attofarad. But those numbers may be too small to reach. However, note that a micron scale device, if properly integrated within microns, can have total capacitances that are much less than a femtofarad. So that the capacitive charging energies do not dominate, we need small devices for low capacitance and very close integration to limit wiring capacitance. In optical systems, there are really 3 reasons why we're using so much energy. First of all, because we have not yet integrated optoelectronics and electronics closely enough and with low enough capacitance. And that's especially true for photodetectors. We really want to reduce the capacitance with which we integrate photodetectors. Secondly, because we have not yet invested enough in the technology. We need low energy optoelectronics, and technologies such as germanium quantum well modulators in silicon photonics are quite possible, but they're not yet technologically available in production processes. But a technology like that could solve a lot of problems for energy. And we also have not invested enough in the specific optics that we really need. Specifically then, we need very low loss optical couplers to make this job easier. And we also need to look at array optics, I mean 2-dimensional arrays of light beams and the optics that would handle that. And the third one is a surprising one perhaps. We use picojoules because we waste picojoules per bit, in the circuits that drive and receive signals. And I'll talk about that as well. This table here shows the energies per bit for many different operations we encounter in handling information, all the way from long-distance communications here down to even the energies required for logic operations in a gate, which are on the scale of a femtojoule, possibly less, possibly more. But the numbers I'm most interested in here are really these ones. Again, we see here communicating off-chip is something that takes picojoules to possibly tens of picojoules for every bit. And also note, data multiplexing and timing circuits take picojoules per bit. A complicated logic operation, such as a floating point multiplication per bit, only consumes about 100 femtojoules, and the energy stored in a DRAM cell is of the order of 10 femtojoules, but the energy to read out a DRAM cell is about 5 picojoules. The dominant point here is that most energy is used for communications, not logic, and that's true even inside machines and all the way down to chips and below. So now let's look at the circuit energies. If the dissipation in the associated circuits is large, then low-energy optoelectronic devices cannot be exploited effectively. So we should stop wasting energy in the electrical circuits we use to run interconnects. For example, in optics, the first thing we could do would be to eliminate the receiver amplifier circuit dissipation. That's typically in the range of hundreds of femtojoules per bit to even picojoules per bit. How could we do that? Well, the key is integrating low capacitance photodetectors close to or beside the transistors. This may eliminate the need for voltage amplification altogether, and we could call that receiverless operation, or perhaps the optimum is about one simple low energy gain stage for near receiverless operation. The energies for receiverless operation are quite interesting to look at. Suppose, for example, that the optical signal we receive is of the order of 1 femtojoules worth of received optical energy. Then that would generate about 1 femtocoulomb of charge. So in a 1 picofarad conventional photodetector, that would generate only about 1 millivolt of signal. In a solder bumped photodetector, which might have the order of 30 femtofarads of capacitance, that would generate about 33 millivolts of signal. But if we have a 1 femtofarad integrated photodetector, we can generate some decent fraction of a volt of signal with no amplification whatsoever. Here is an example showing photodetectors integrated right beside the gate of a transistor. That might be the ideal end goal, although the arguments we're making here would work even if we had to go through a few microns of wire, such as the thickness of the wiring layers on an integrated circuit, to connect the transistor to the photodetectors. To repeat some of the arguments here, we should integrate the optoelectronics beside the transistors, that is, within a few microns at most. This allows excess capacitance in the scale of only hundreds of attofarads. Photodetector elements on scales of 1 micron or less dimensions allow detector capacitance itself to be of the order of 100 attofarads, and transistors, since they have input capacitances of tens to hundreds of attofarads, therefore leave us with the possibility of having less than 1 femtofarad total capacitance with this kind of integration. Time multiplexing takes energy. For example, picojoules per bit in SerDes or serializer deserializer circuits. Why does time multiplexing take energy? First of all, because we touch a bit many times to time multiplex or demultiplex it. For example, we move it in registers and buffers. If we estimate something on the scale of 1 to 100 femtojoules per bit for every time we touch a bit, we quickly get to picojoule per bit energies. Because we run some of the circuits at very high speed, we have a second reason why we take more energy in time multiplexing, because such high speeds require even more energy per bit operation. And thirdly, because we also have to perform clock and data recovery, or CDR, for synchronization, we take more energy. That process similarly takes picojoules per bit in those circuits. If we go on to look at other things we might do in links, for example, the use of advanced multi-level signaling, that only requires more circuitry and energy. Any use of error correction only requires more circuitry and energy. So time multiplexing and advanced signaling to get more information per channel only make the energy per bit problem worse. Why do we use such circuits? There are two reasons. First of all, because we think we're limited by the number of available channels for interconnection. For example, the number of fibers. That forces a maximum wavelength multiplexing, but also time multiplexing. And secondly, because we think we cannot run large systems synchronously, so we need the clock and data recovery. But neither of these beliefs are actually correct. Optics can help us avoid both of these apparent problems. First of all, on the issue of synchronous systems, one thing that optics allows is very predictable time delays, and we'll come back to this. And that means we can, in fact, run quite large systems synchronously and hence eliminate all of these clock and data recovery energies. And that's especially true if we're anyway running at low clock rates. But how could we run at low clock rates and still get enough information through? The trick there is to move to using free space optical systems with thousands to tens of thousands of connections. There is nowhere else we can get 3 or 4 orders of magnitude of headroom for very little cost. And that would enable us to avoid time multiplexing and all the SerDes energies because we could run large numbers of channels at low clock rates. So we could run at the energy efficient clock rates that transistors like to run at of a few gigahertz to possibly about 10 gigahertz or so. So let's look at this issue of how many spatial channels there are for communicating between two surfaces. We imagine that we have a transmitting surface of area AT and a receiving surface of area AR. Then the number of possible optical channels, spatial channels, per polarization between two surfaces of these areas, separated by some distance L, at a wavelength lambda, is limited by diffraction to give this number of channels, which is the product of the two areas divided by the square of the separation and the square of the wavelength. The derivation of this is given in some detail in this reference here. For example, at 1 micron wavelength, for two surfaces each of area 10 by 10 centimeters separated by 10 meters, there would be 10 to the 6 possible spatial channels. So that's like having two telephoto lenses staring at one another over a distance of 10 meters. That optical system could handle 10 to the 6, a million spatial channels. Suppose we look then not at such a rack-to-rack communication, but at chip-to-chip communication, so on a centimeter scale. Then, for example, for two surfaces separated by a couple of centimeters and using 2 by 2 millimeter areas on those surfaces as the optical areas, then we would get 4 times 10 to the 4 possible channels. Now, you might think it's hard to work with tens of thousands of light beams, but in fact, most of this technology has been about for at least 30 years. For example, we can easily generate large arrays of light beams from one source. Diffractive optics has done this for a long time. And free space beam arrays, as I said, have the same time delay to picosecond levels over millions of pixels. And remember, we do work with millions of pixels quite routinely with free space optics, such as the camera in your cell phone. Aligning an entire array of light beams is not actually much more difficult than aligning one beam. So this one alignment gives you 10,000 beams aligned. All we have to do is add array orientation, the twist of the array, and some overall array dilation, that's the size of the array physically. If necessary, we could servo the alignment in free space arrays, which we can do even in physically demanding situations. For example, think of the servoing of the optics in a CD or DVD player. That's a spinning disc, and we manage to keep the beam aligned within less than a micron. To give some sense of how this would all be put together, I put together a strawman system. So this is sketched over here at various different levels, from photodetectors possibly beside transistors, up through the wiring layers of the integrated circuit, to an optical interposer layer, a silicon photonics layer, which you see in light blue in these various parts of this complicated diagram. So a key additional technology to make this work is indeed some integration, which should be at least hybrid, and a silicon photonics interposer layer would be particularly useful. We would put the optoelectronics mostly or totally in this layer and hybridize that directly on top of some silicon integrated circuit. With this, we'd be able to implement the ideas I'm talking about. And that silicon photonics interposer layer would work particularly well if we added some materials to it, for example, germanium for germanium quantum wells, or possibly 3-5s, because then we could easily get to the energies we're looking for in the optoelectronic devices without having to use high-Q resonators, for example. And as I've said, we would put detectors beside the transistors or in the photonics interposer layer on top. We would also want improved optical couplers in this system, so things like optical vias perhaps through the silicon wiring layer, but certainly waveguide arrays and, most importantly, efficient free space couplers. A major opportunity here is indeed to try to exploit nanophotonics to make beam and mode couplers with percents of loss, not decibels of loss. The goal here is to get to 10 femtojoules per bit of total system energy up to, say, 10 meters of distance. Note that this strawman system I put together here predicts that even with 19 decibels of total optical system loss, that's what I put into the calculation, 10 femtojoules per bit is still achievable. Note incidentally that 10 femtojoules per bit implies only 10 milliwatts of power dissipation for 1 terabit per second of interconnect bandwidth. Well, I had promised that there was something I said we had to stop doing, and by now it should be quite clear. I've been arguing that to reach 10 femtojoule per bit system energies, we essentially have to stop time multiplexing, especially to high rates. If we don't do that, we can't get rid of these picojoule per bit energies in the electronic circuits. The same is true about thinking about complex modulation formats that would require some complex coding and decoding. We can't afford the circuit energies for that. What we have to start doing? Well, we have to start integrating, as I said, within microns, and we have to start using more optical channels. Certainly wavelengths and large numbers of them. I've been advocating here for the more radical idea of free space optics, but I'm not arguing against using lots of wavelengths. The free space optics offers us a possibility of truly large numbers of channels, tens of thousands or more. It really has tremendous headroom. Another piece of good news is we don't need any new physics. The mechanisms we already have are more than good enough. More good news is that we know what technology we need. We want this integration technology, a femtofarad level integration technology. We want low energy modulators. We need to implement the ideas we have. We also need to improve couplers. Loss in couplers translates directly by the same factor into increases in system energy. And I'm arguing we should look again at implementing array optics. This could really work and give us very large numbers of channels. Now, another piece of good news is I think we would want to implement much of this technology anyway. And I'm saying that the real good news is that we have the potential for orders of magnitude of possible improvement. We really can eliminate the picojoules per bit circuit energies by using large numbers of channels. Remember, as I said, that free space optics allows thousands to possibly even millions of channels. And I'm saying we really could change from the 1 to 10 picojoule per bit towards 10 to 100 femtojoules per bit. That's total energy for all interconnects from 1 centimeter to 10 meters. The other piece of good news is there simply is no other competitive solution. Optics is the only way to increase the interconnect bandwidth and reduce the energy for off-chip interconnects. Thank you for your attention.